Today I'd like to talk about regression inference. So please open up your study guide to this particular section. Now let's begin with the regression model example. Now how much would an adult female weigh if she were 5 feet tall? She could weigh varying amounts. In other words, there is a distribution of weights for adult females who are 5 feet tall. This distribution is normally distributed, we hope. So as long as we have a large enough distribution, we're going to assume that weights will be normally distributed. What would we expect for other heights? And once again for other heights, we would expect that these distributions as well would be normal. So where would you expect the true least squares regression line to be if we were to associate height versus weight? Now, since we are expecting normal distributions for each one of these heights, we're going to expect our least squares regression line to be at the means of all these normal distributions. So, our least squares regression line can be represented by the model mu sub y equals alpha plus beta x, where alpha represents the y-intercept of our least squares regression line and beta represents the slope. Now what about the standard deviations of all these normal distributions? We would want the standard deviations of all these normal distributions to be approximately the same. Now this leads us to our regression model. Now the mean response mu sub y has a straight line relationship with x such that mu sub y equals alpha plus beta x. This is our least squares regression model from the population of all values of our bivariate data, where the slope beta and the intercept alpha are both unknown parameters. Now for any fixed value of x, the response y varies according to a normal distribution. Repeated responses of y are independent of each other. And the standard deviation of y, which we'll call sigma sub y, is the same for all values of x. Sigma sub y is also an unknown parameter. Now we use the model y hat equals a plus bx to estimate the population least squares regression line mu sub y equals alpha plus beta x. The slope b of the least squares regression line, based on our sample data, is an unbiased estimator of the true slope beta. So if we were to take all possible samples of a particular size and create all the possible least squares regression line based on the sample sizes with that bivariate data, the average of the slopes would be equal to beta, our true population parameter for the slope of our least squares regression line. Likewise, the intercept A of the least squares regression line is also an unbiased estimator of the true intercept alpha. A and B are both unbiased estimators of our least squares regression model. Creating least squares regression lines from a particular sample and continuing to do it over and over until we've taken all possible samples of that particular size would lead us to several different least squares regression line models. And the average of all the slopes and the average of all the y-intercepts will lead to the true parameter value of alpha and beta. Now the standard error S is also an unbiased estimator of the true standard deviation of y. And the formula for the standard deviation of our least squares regression line model can be found by taking the square root of the sum of the squared residuals divided by n minus 2. Notice when we divide by n minus 2, we're basing this on the degrees of freedom for this particular model. The degrees of freedom is equal to n minus 2 since we lose 2 degrees of freedom for estimating both parameters alpha and beta. So when we estimate more than one parameter, we're going to lose an additional degree of freedom. Therefore, the denominator here is going to be n minus 2. Now let's talk about the sampling distribution for beta. Now suppose we took many samples of the same size from this population and then calculated the least squares regression line based off of each one of those samples. Now if we did this, we would get several least squares regression lines. Here's some possible least squares regression lines based upon some of our sample data. Now using the slope from each of these least squares regression lines, we can create a sampling distribution for the slope of the true least squares regression line for our population. So let's go ahead and plot all the slopes from the sample of least squares regression lines here. Now although we don't have many, this is just a visual example here, but if we were to continue to do this process over and over and over again for larger sample sizes, what shape would this distribution ultimately have? Well, since B is an unbiased estimator of beta, we would expect that the sampling distribution here would be approximately normal. Now, what does the mean of the sampling distribution equal? And once again, the sampling distribution is based off the value of B, the slope of the least squares regression line, based off of our sample data. And the collection of all possible B's from all possible least squares regression line made from a particular sample size would create a normal distribution, and the mean of that particular distribution would be equal to the population parameter beta. So the mean of all slopes of the least squares regression line for samples of a particular size is equal to the actual true parameter value beta for the least squares regression line based off all bivariate data from the entire population. Now, what's the standard deviation of this particular sampling distribution? The standard deviation of the sampling distribution for B is given by the following formula. And notice we call it S sub B sub 1. Now on your formula pages, B sub 1 is denoted as slope. And S sub B sub 1 is the standard deviation for the slope of our least squares regression model. And that can be found with the following formula. We can take the square root of the sum of the differences of our actual observed y values minus the predicted y values divided by n minus 2, and divide that by the square root of the deviations of x squared. And notice that the numerator is actually equal to the standard deviation of our model divided by the same denominator, which is the square root of the sum of the square deviations. Now these formulas seem very complex. Typically we don't have to use these formulas in a calculation process for standard deviation. We're usually given the standard deviation of the slope based on table data and information that's given to us based off computer generated output. Or we can work our way back into it knowing the t-test statistic value for a hypothesis test, and we can work backwards into calculating the standard deviation of the slope for the least squares regression line model. And we'll take a look at that strategy later. Now let's talk about the conditions for regression inference on slope. Now our conditions for inference for regression is a little bit more difficult than the other conditions that we have talked about for other inference procedures. We begin with independent observations. Now we're going to assume in our regression model that the observations are independent of one another. To check that the observations are independent, we need to make sure that we have an SRS of data. So if we have an SRS of data, we can assume that we have independent observations. Then we need to establish that our sampling distribution has a linear relationship. Is there a true linear relationship? We can test for a true linear relationship by checking the residual plot and looking for a random scattering of points. Recall in linear regression that we understood that models were truly linear if their residual plots were randomly scattered with no apparent pattern. Next, we need to take a look at constant standard deviation. The standard deviation of a response variable should remain constant. To see if our standard deviation of the response is constant, we're going to check the scatter plot. And when we look at the scatter plot together with the least squares regression line, we need to make sure that the points about the least squares regression line are evenly spaced. Do our points bounce back and forth across the least squares regression line, producing a constant standard deviation for our response variable? And finally, responses vary normally. The responses need to vary normally about the true regression line, And to check to see if the responses vary normally, we're going to take a look at the box plot of our residual values. And when we graph the box plot, we want to take care and make sure that it's fairly symmetrical with no outliers. And if it is, there's no reason for us to doubt that the responses would vary normally about the true regression line. So once again, 4 conditions for inference: independent observations, linear relationship, constant standard deviation, and responses vary normally. Now let's talk about the confidence interval for a linear regression model. Here's the formula for the confidence interval for the slope of the least squares regression line. We're going to take our point estimate here, B, and add or subtract the critical value, T star, times the standard deviation of our statistic, B, which we're going to call S sub B sub 1. And that's going to give us the confidence interval for the slope of the least squares regression line. The critical value and the standard deviation of the statistic together make up our margin of error. So once again, we begin with our point estimate. Our best guess for the true slope of the least squares regression line for the entire population is the slope of the least squares regression line based off of our sample data. And once again, we're going to add or subtract this component called margin of error, which is made up of a critical value times the standard deviation of the statistic we use to estimate the parameter, which is B. Notice that the degrees of freedom is going to be equal to n minus 2. Once again, for our T star value, when we calculate it, it's based off a T distribution that has n minus 2 degrees of freedom, since we lose 2 degrees of freedom by estimating both alpha and beta in the least squares regression line. Now here is the test statistic value we calculate for the slope of the least squares regression line. Once again, generically, our test statistic value is equal to the statistic we use to estimate the population parameter minus the parameter of interest itself divided by the standard deviation of the statistic. Now our test statistic value for a regression inference will always be T. The statistic that we use to estimate the population parameter is B, based off of our sample data, the slope of the least squares regression line. The parameter itself is beta, the true slope of the least squares regression line, based off the population data. And the standard deviation of our statistic B is S sub B sub 1. So recall the very complex formula for S sub B sub 1. Our calculator will give us the t-test statistic value, and we can work backwards into the value of the standard deviation of our slope, S sub B sub 1. So by using this test statistic value formula, it's often helpful to calculate the standard deviation component. Once again, B represents the statistic we use to estimate the population parameter. The population parameter itself is beta, and the standard deviation of our statistic is S sub B sub 1. Notice again that degrees of freedom for our t-test statistic value is n minus 2. We lose 2 degrees of freedom once again because we have 2 parameters in our least squares regression line model, alpha and beta, and we lose 2 degrees of freedom for estimating both those parameters. Now the hypothesis statements are pretty much the same. Here is the null and alternative hypothesis we use for the slope of the least squares regression line inference test. Now we begin in the null hypothesis by assuming that beta is equal to 0. This implies that there's no relationship between x and y. If we have a slope of 0, we don't have any linear relationship, or that x should not be used to predict y. So we always begin in the null hypothesis on linear regression tests by assuming that there really is no linear relationship between our 2 variables. In other words, the slope of the least squares regression line would be 0. Now we could do a right-tail test and check to see if the slope of our regression line is positive. Or we could do a left-tail test if we wanted to test to see if the slope of the least squares regression line is negative. Or we could do a two-tail test just to see if there's a linear relationship between our 2 variables. In other words, if there were, our slope of the least squares regression line would not be equal to 0. So once again, we have one-tailed and two-tailed tests, and it's all going to be based upon the context of the problem. Now don't forget you need to define beta, the population parameter, in context of the problem. So we always want to say where beta is the true slope of the least squares regression line for, and then go ahead and finish that off based on the context of the problem itself. So once again, we've got H0 and HA, and then we want to define the parameter of interest in context of the problem. And here our parameter of interest is beta, the slope of the least squares regression line. Always start in H0 by assuming that there's no relationship between the two variables. In other words, if we were to create a least squares regression line, the slope would be 0 because there's no linear relationship. And then in HA, understand what you want to do. Do we want to do a one-tail or a two-tail test? Are we checking to see if there's a positive relationship, perhaps a negative relationship, or is there just a relationship in general? And if that's the case, of course, we would use a two-tailed test. Positive relationships imply that we have one-tailed right-tailed tests, and negative relationships or associations imply that we have a one-tailed left-tailed test. Now let's begin with example 1 here. It's difficult to accurately determine a person's body fat percentage without immersing him or her in water. Researchers hoping to find ways to make a good estimate immersed 20 male subjects and then measured their weights. Find the least squares regression line, the correlation coefficient, and the coefficient of determination using the following table of data. So let's take a look at our table data here, and let's go ahead and find the least squares regression line, the correlation coefficient, and the coefficient of determination. So the first thing that we want to do is we want to populate list 1 with weight, and let's populate list 2 with body fat. Now, once our data has been populated into our calculator and it's been checked, we're going to go ahead and calculate the least squares regression line. Now, recall to calculate the least squares regression line based on bivariate data, we're going to go ahead and do a stat and a calc. And instead of choosing option 4, I'm going to bypass option 4 and choose option 8, which is also linear regression. However, they write the y-intercept first and the slope second, and this is more conventional when we talk about the convention on writing least squares regression lines for AP statistics. Now I don't need to press anything here because the default is list 1 comma list 2. Those are the two data lists that we put our information in. So our least squares regression line here, based on this bivariate data, is going to be y hat equals negative 27.376 plus 0.250x. Now recall, when we're writing the least squares regression line, we need to define our variables here, where x here represents weight in pounds and y represents body fat in percent. Or we could write the least squares regression line using our variables here, where we say body fat hat is equal to negative 27.376 plus 0.250 times weight. So sometimes you can write these descriptively as well. Now let's go ahead and take a look at the correlation coefficient. Now notice when I did my linear regression, it didn't give me the value of r or r squared. So I want to make sure that my diagnostics are turned on. So let's go to catalog here. If I go second 0, if I choose my catalog option here, I want to toggle down to the D's. I can either just keep arrowing down until I get to the D's, or I can press D and it'll take me right there. But if I get down to the D's, I want to check for my diagnostics here. And I want to make sure that my diagnostics are turned on. Press enter again on the home screen and that's done. Now let's rerun the regression here. So we're going to do stat, calc, and then we're going to do, once again, option 8. We're going to do a linear regression between list 1 and list 2. And now it's going to give us the value of r and r squared. Now our correlation coefficient r comes out to be 0.697. Now recall that correlation measures the strength and direction of a linear association. And then if we square the correlation coefficient, we get the value of r squared. R squared is equal to 0.485. And we'll go ahead and interpret the coefficient of determination on the next page. Now once you've found the least squares regression line, the correlation coefficient, and the coefficient of determination, let's go ahead and explain the meaning of the slope in context of the problem. Does the y-intercept of the least squares regression line have meaning in context of the problem? Explain the meaning of the correlation coefficient in context of the problem. And then explain the meaning of the coefficient of determination in context of the problem. So this is really a review from Chapter 5 from our regression section. So let's take a look at the meanings for each one of these. Okay, so in example 2, let's go ahead and start with the meaning of the slope in context of the problem. Remember, once we have our least squares regression line, we're going to say that for every 1 unit increase in x, there's going to be a slope increase or decrease in y. And that's all dependent upon the sign of the slope, whether we're increasing or decreasing. So in this case, we can say, for every 1 unit increase in x, now recall x was weight measured in pounds. So for every 1 pound increase in weight, there is a slope. Now our slope here is 0.250, so we're going to put 0.250 here. So there is a 0.250, and once again our slope's positive, so we're going to say increase here in our response variable y. So for every 1 pound increase in weight, there is a 0.250 increase in body fat percent. Now, does the y-intercept of the least squares regression line have meaning in context of the problem? Recall, to find the y-intercept, we let x be 0. Does it make sense to have a y value, a body fat value of negative 27.376 based on an individual that has a weight of 0 pounds? Well, it doesn't make sense to have a weight of 0 pounds, and it doesn't make sense to have a negative body fat percentage. So there really is no interpretation of the y-intercept in this particular problem. So, does the y-intercept of the least squares regression line have meaning in context of the problem? No, it does not. X equals 0 has no meaning. Now explain the meaning of the correlation coefficient in context of the problem. Once again, we saw that the value of r was 0.697. We have a moderate positive linear association between x and y. Now x and y in context, once again, is weight and body fat percent. Recall, the magnitude of r determines the strength. And once again, if it's between 0 and 0.5, it was weak. 0.5 to 0.8 was moderate. And 0.8 to 1 was strong. Now finally, explain the meaning of the coefficient of determination in context of the problem. Now the square of the correlation coefficient, which we did on the earlier page, once again, was 0.485. Now to interpret the coefficient of determination, recall that approximately r squared percent, or 48.5% of the variation in our response variable y here once again is body fat percent. So approximately 48.5% of the variation in body fat percent can be explained by the least squares regression line of x and y, which is weight and body fat percent. In other words, how much was our model improved by going from a 1 variable only model to a 2 variable model? So once again, if I go back to my table of values here, if we were just trying to predict body fat percentage based on these 20 male subjects, my best guess would have been the average of all these values. So if I had to guess what body fat percent would be for the next individual, my best guess would be the average of all those. Now, how much did my model improve by incorporating a new variable, weight? Based on weight, here are some body fat percentages. So based on our least squares regression line, approximately 48.5% of the variation in body fat percent can now be explained by the linear regression of both weight and body fat percent together. Now in example 3, they want us to estimate alpha, beta, and sigma for our problem. Then let's create a scatter plot for the data, and then let's create a residual plot for the data. Okay, let's begin with the estimates for alpha, beta, and sigma. Now, recall that our best guess for alpha here is going to be equal to A, our point estimate A. And once again, our point estimate A is the y-intercept of our least squares regression line, which when we calculated, recall, our least squares regression line the actual y-intercept was negative 27.376. Our best guess for beta is the point estimate B based off of the sample data that created our least squares regression line. And once again, the slope of the least squares regression line was 0.250. The standard deviation, once again, is the square root of your squared residuals divided by n minus 2. Our calculator will actually calculate that for us so we can get the standard deviation for this least squares regression model. And so I'm going to kind of jump ahead here to calculate that standard deviation component by going stat and over to test. And then I'm going to go ahead and toggle up so I can get to the second page, because one of our last test options is the linear regression t-test and the linear regression t confidence interval. I'm going to choose option F. Now, I got my data in list 1 and list 2. The frequency default is 1 still. Doesn't matter what test I choose because I'm not doing it yet. But if I do a calculation, several things happen in this linear t-test calculation here. It will give me my t-test statistic value. It will give me the p-value. It will give me the appropriate degrees of freedom, sample size minus 2. And then here are my estimates for my slope and my y-intercept. The y-intercept is negative 27.376 and the slope is 0.250 to 3 places. And then the standard deviation of our model, if we square the residuals and divide by n minus 2 and take the square root of that, it's kind of like taking the variance and taking the square root of the variance to get the standard deviation. We get a standard deviation of 7.049. The standard deviation really represents how far on average each of those points are away from the least squares regression line. So some of them have positive deviations, some of them have negative deviations, but recall if I summed up the deviations, they'd all be 0. So we square it to make it a tangible measure, and then once we take the average by dividing by n minus 2, since we lose 2 degrees of freedom, we get it back into alignment by taking the square root of that value, and we get an appropriate standard deviation for our model. The standard deviation here really represents how far each of our data points away from the least squares regression line. So on average, this would be kind of an average measure of our residuals. Now let's go ahead and create the scatter plot here. So to create a scatter plot, I'm going to go ahead and turn my stat plots on. I'm going to go ahead and choose the scatter plot option. My data is in list 1 and list 2. And if I do a zoom 9 option, I'm going to get a scatter plot of data. It appears that there is a positive linear association. It's not strong, but recall the value of our correlation coefficient was moderate. We had a correlation coefficient value of 0.697, so we had a moderate positive linear association. Since we've already done our least squares regression line on our calculator, we can go ahead and superimpose the actual least squares regression line with the scatter plot by calling up y equals and going through the following series of keystrokes here. We're going to take vars for variables, go down to the statistic variables in option 5, so vars 5, and then go over to EQ for equation, and then go ahead and select regression equation. And the regression equation is the one that you previously did on your calculator. It stores that internally for you. And then I'm going to go ahead and graph that together with my scatter plot. So there's the scatter plot and the least squares regression line together. Okay, so you may want to make a sketch of that, and you can somehow create your axis here and try to estimate what your y-intercept would be, create your least squares regression line, maybe put your equation here, y hat equals negative 27.376 plus 0.250x. Maybe label your axes here. We're going to let x here once again represent weight in pounds, and we're going to let y represent body fat in percent here. And then you can kind of see how these points go. So, try to do the best you can by recreating this scatter plot. Now, I'm not going to draw it exactly to scale, but I'm going to try to make sure that I've kind of got all my points placed appropriately on it. So we get a good idea of really what the graph looks like based on a quick sketch of it. Now, to create a residual plot, recall that we need to calculate the residuals. The residuals once again represent how far each one of the observations are away from the least squares regression line. So we always like to plot our residuals either versus x or our predicted value y hat. I'm going to plot my residuals here versus x, which is our weight variable. And we're going to let the y-axis here be the residuals. Recall the residuals are the actual values minus the predicted values, okay? It's how far each of these actual points are away from what the predicted points would be on the least squares regression line. That represents the residual. So we can do a residual plot here by going into our list here and going stat, edit, and I'm going to go ahead and list 3, jump up to list 3, and I'm going to go ahead and choose my second list option, because once I've done my least squares regression line on my home screen, I can toggle down now and select the residuals based off that least squares regression line. And then go ahead and press enter, and here are our residuals. Some residuals will be positive, some will be negative. We know the sum of the residuals because it is our line of best fit with least squares regression. The sum of the residuals will be 0. And let's go ahead now and plot the residuals here together with x. So I'm going to plot x in list 1 versus residuals in list 3. Now, before I actually do a zoom 9, I'm going to go to y equals. I'm going to unhighlight the equal sign so I don't see that regression line in the way. And then let's go ahead and do a zoom 9 option. So here's a residual plot. Recall that our residual plot has positive and negative values. So some are positive and I have some negatives down here. I'm kind of just briefly sketching some of this in here the way I see it. I've got some close to 0, one up and one down here. Now, the nice thing about this residual plot, my residual plot is randomly scattered. It's pretty much scattered about the x-axis. So that's a good thing, because a randomly scattered residual plot indicates that our data truly is linear. Now let's take a look at example 4. Once again, we have the same type of problem here. We immerse the 20 male subjects and then measure their weights. Now, is there sufficient evidence that weight can be used to predict body fat? So let's begin example 4 with our conditions for inference. Now recall, this is probably the hardest part of regression inference because there's 4 of them. Let's begin with the first one. Now in the first one we can say that we have an SRS of 20 males where body fat and weight are measured. And based on that SRS of data, we can assume that the observations are independent. Now condition 2, we need to establish that we have a true linear relationship. So by checking the residual plot, and once again we looked at the residual plot earlier, since the residual plot of sample data is randomly scattered, we have a true linear relationship. Next we need to check for a constant standard deviation. So we're going to check the scatter plot to see if the points are evenly spaced across the least squares regression line. Recall in our graphical display, and if I go back and take a look at that, once again here is our residual plot. The residuals were randomly scattered, so we did have a true linear relationship there. Now if I go back and highlight this again on y equals, and then let's go back to our stat plot, and let's go ahead and plot together with the least squares regression line the scatter plot of our data values, list 1 versus list 2, our bivariate data here. And let's take a look at a zoom 9 option now. Okay, notice that the points are pretty much evenly spaced across the least squares regression line. So the least squares regression line together with the scatter plot is going to indicate that we do have a constant standard deviation here. So since the scatter plot of points is evenly spaced across the least squares regression line, the standard deviation of the response is constant. And finally, in our fourth assumption, we need to make sure that our response is varying normally, and we can check that out by taking a look at the box plot of our residuals. So going back to our calculator here, once again my residuals were in list 3. So I'm going to go ahead and unhighlight this once again so it's not in the way. I'm going to go to second stat plot, and instead of doing a scatter plot now, I'm going to go ahead and choose a box plot option, a modified box plot here. And I'm going to go ahead and do a modified box plot of list 3, which are my residuals. And now let's take a look at the box plot of our residuals. So if I do a zoom 9 option, this gives me the box plot of my residuals. Now I can go ahead and sketch that box plot of my residuals. Okay, so we kind of have a long left whisker here, and a fairly big box. You don't have to really draw the scale to this, but it almost looks fairly symmetrical where the median is inside the box, and then maybe a little bit shorter right whisker. But overall, that's fairly symmetrical. And so I'm going to say now, since the box plot of residuals is fairly symmetrical with no outliers, the responses vary normally about the least squares regression line. So now our conditions for inference have been met. Now let's go ahead and take a look at our hypothesis statement. Recall, we're trying to find out if there's enough evidence that weight can be used to predict body fat. So we're going to begin in H0 and assume that there really is no linear relationship at all. And if there is no linear relationship, then the true slope of our least squares regression line would be 0. In HA, I want to really see if there is a linear relationship. Can we use weight to predict body fat? In other words, is there a slope to my least squares regression line? So I'm going to perform a two-tailed test here, where beta is the true slope of the least squares regression line for weight and body fat. Now let's go ahead and do our calculations. Once again, our calculations come in two pieces. Let's begin with the test statistic value. Our test statistic value, once again, is a t-test statistic value. The estimate we're going to use to estimate the slope is b, based off of our sample data, the slope of the least squares regression line from our sample data, minus beta that we assume in the null hypothesis, divided by s sub b sub 1, which is the standard deviation of b, our statistic we're using to estimate the parameter here. Now, we can fill all the pieces in except for this standard deviation piece, and I'm going to show you how we can kind of work backwards into that. Now, once again, b represents the slope of our least squares regression line, and at this point, I would just go ahead and do the full-blown test here. So we're going to go stat, and we're going to go over to test, and I'm going to toggle up and choose the linear regression t-test, which is option F. Once again, our data is in list 1 and list 2. Frequency default is 1. We're doing a two-tail test, so we'll choose this option here. No need to type in your regression equation. It'll calculate it for you. Let's do a calculation here. And notice that our t-test statistic value, and I'll just write it down right now, is 4.120. Let's go ahead and write in the other pieces here. So t is equal to b. Now once again, b was the slope of the least squares regression line based off the sample data, which was 0.250, minus beta that we assumed in the null, which is 0, divided by s sub b sub 1. Now, if I know this piece here is 0.250, and I know my t-test statistic value is 4.120, then I can solve this a simple equation here for s sub b sub 1. So s sub b sub 1 really is equal to b, which is 0.250, minus 0 divided by 4.120. If I'm able to take the test statistic value that I got from my calculator here and use it to work backwards into the standard deviation, I get 0.25 divided by 4.12, and so I get a pretty good estimate of s sub b sub 1, which is 0.061 to 3 places. So I can now go ahead and piece this back in here, and so my t-test statistic value turns out to be 4.210. Now, recall the second piece of the calculation is the p-value. The p-value, once again, is the probability that the test statistic value could be this extreme or more. And recall, since we're doing a two-tailed test up here, we need to multiply that by 2. So, although our t-test statistic value turned out to be 4.120 standard deviations above the mean, I need to locate t equals negative 4.120, and I really need to double that tail region. So we're going to take 2 times a t-CDF, accumulate area from 4.120 up to infinity, based on a t-curve that has 18 degrees of freedom. Recall that our degrees of freedom is equal to our sample size minus 2, since we lose 2 degrees of freedom in a linear regression test, since we're estimating both parameters alpha and beta. And of course the p-value here based on my test here, once again I'll go stat and test and go back up to the linear regression t-test here. The actual p-value turned out to be 0.0006. So in conclusion, since the p-value of 0.0006 is less than alpha, I'm going to assume alpha is 0.05, that's significant. We reject H0. There is sufficient evidence to suggest that basically beta is not equal to 0. In other words, we do have a linear relationship. And go ahead and answer it exactly like they asked it. Is there sufficient evidence that weight can be used to predict body fat? There is sufficient evidence to suggest that weight can be used to predict body fat. Now let's take a look at example 5. Once again, we're going to use the same example with the bivariate data of weight versus body fat percent. And we want to this time find a 95% confidence interval for the true slope of the least squares regression line. Now once again, the conditions for inference remain the same. We've done the conditions for the hypothesis test, so I'm going to go ahead and bypass the conditions here and get to the calculations. Now recall that for a confidence interval, we take our estimate plus or minus our margin of error. And our margin of error, once again, is made up of two pieces. It's made up of the critical value times the standard deviation of the statistic that we're using to estimate the parameter. So in this case, our confidence interval here is equal to our estimate, which is B, the slope of the least squares regression line based off of our sample data, plus or minus our critical value, which is T star, times S sub B sub 1, the standard deviation of our statistic. Recall from earlier, and if we go back and look at the hypothesis test here, we did find the value of S sub B sub 1. Okay, remember how we worked backwards into it and found the value of the standard deviation for the slope of our least squares regression line by getting the t-test statistic value from the hypothesis test and then solving for S sub B sub 1 based on our null hypothesis. And when we calculated S sub B sub 1, we came out with a value of 0.061. So recall that our slope from our least squares regression line, our best estimate for beta, was 0.250. We're going to add or subtract our critical value and then multiply by the standard deviation of B, which we calculated in the previous problem, once again, S sub B sub 1, to be equal to 0.061. The T star value is based on a 95% confidence interval. So once again, I'm going to go ahead and draw a T-curve here, and I'm going to allocate the middle region here with 95% for my 95% confidence interval. That's going to leave me with 2.5% for my tail regions, and the upper T star value is the T-score associated here with the 97.5th percentile. So I can do that by using the inverse T function at the 97.5th percentile based on a T-curve, once again, that has 18 degrees of freedom. So let's go ahead and calculate that. So we're going to go second distribution, inverse T. I want the 97.5th percentile of a T-curve that has 18 degrees of freedom. And recall, degrees of freedom is equal to the number of bivariate pieces of data that we have minus 2, since we're losing 2 degrees of freedom because we're estimating both alpha and beta in our least squares regression line. So that gives us a T star value here of 2.101. Now I have the pieces for my confidence interval, and I can go ahead and calculate that. So let's take that T star value and multiply it by S sub B sub 1, which is 0.061. I'm going to store that margin of error into variable x here. And let's take our point estimate of 0.250 and let's subtract x. And let's take our point estimate of 0.250 and let's add x. And so my confidence interval here for the slope of my least squares regression line is going to go from 0.122 up to 0.378. Now, in conclusion for a confidence interval, we can now say that we are 95% confident that the true slope of the least squares regression line is between 0.122 and 0.378. So if we were trying to see if weight could predict body fat percentage, we could definitely here reject H0 since 0 is not in our interval. Obviously there's a slope to this least squares regression line, so there is a linear relationship that we can establish between body weight and body fat percent. Let's go ahead and verify this confidence interval by doing a linear regression confidence interval. So I'm going to go stat, I'm going to go to test, I'm going to toggle up here to the linear regression t-interval. Once again, my data is in list 1 and list 2. I want to do a 95% confidence interval. And when we calculate, notice our confidence interval here on calculation matches up. It goes from 0.122 to 0.378 to 3 places. So now we've done both a hypothesis test and a confidence interval for least squares regression. And finally, I want to go to the last section here, which is on computer-generated data. Now here's the computer-generated results from our bivariate data from the previous example. Once again, we had n equals 20 observations. The coefficient of determination was 43.83%, and the standard deviation of our least squares regression model was 7.049. Now in the table, we're given parameter values for the intercept and the weight. We're given estimates and we're given standard error components. Based on our sample size, what is the appropriate degrees of freedom? Once again, for a regression test, we're going to take n-2 for degrees of freedom, since we lose 2 degrees of freedom because we're estimating both parameters alpha and beta. So our degrees of freedom here will be 18. Now, to calculate the correlation coefficient, the first thing we want to do is we want to take the value of r squared and convert it to a decimal. So we want to rewrite 43.83% as 0.4383. Then, to calculate the correlation coefficient, we're going to take the square root of that value. Now, recall the square root of r squared is the absolute value of r. So our correlation coefficient could be positive or negative. To determine the sign of the correlation coefficient, we need to take a look at the slope of our least squares regression line. Since our slope is positive, our value for our correlation coefficient will be positive as well. Now, what does the S represent in context here? Recall that S is the standard deviation of our model. 7.049 represents the average of the deviations based on our degrees of freedom. So if we took a look at a scatter plot and our least squares regression line, then the distance that scatter plot those points are from the least squares regression line on average represents the standard deviation of the model. Now what do these numbers below represent? For our intercept and our weight, notice these are the values of A and B. This is the value of the y-intercept of the least squares regression line, and we have the slope of the least squares regression line, which is based on our variable weight. So once again, we can build our y-hat value, our least squares regression line, by taking negative 27.376 plus 0.250x. So once again, these numbers represent the actual coefficients of our least squares regression line. Now what about this number down here? What does this number represent? Now notice that these are the standard error components both for your intercept alpha and your weight, which is your slope, beta. So this is S sub b. And notice that S sub b sub 1 is given here in the table, your standard error component. And if we were to do a confidence interval or a hypothesis test on alpha, this is the standard error that we would use to test it. So table entries are very nice because they give us some very difficult values to calculate. In particular, we have the standard deviation of the slope of a least squares regression line given to us in our standard error component under the parameter weight. So 0.061, once again, represents S sub b sub 1. This concludes our lesson on linear regression.